So we're not going to have a lab today, but we are going to meet. And what we're going to do, I'm going to make it actually into a 2-lecture period. I'm going to give you a 10-minute break in between like you normally would with classes. So we'll meet this afternoon at 1:20. I'll lecture. I'll kind of go over some theory part. You have a 10-minute break, like normal. And then we'll meet back again. Then I'm just going to do examples of basically what we did. So you can get go over stuff. And that'll more or less get us caught up for the semester and we'll be in good shape. So our final is actually scheduled for I think almost the last day. The times, so in other words, in physics 125 and 126, we always have a special time slot. There's a historic reason for this, but I won't go into it. The only problem with that is I know that whenever a final, I think if you're to plot final exam grades versus day in the week, finals week, I think they just drop like a rock. I think at some point that last final, when you have it, you have that last final in your hand, and you know as soon as you hand that in, you can go home. And at some point you don't really care because basically you want to go home, and that final is preventing you from going home. And so how would you feel if instead we have actually, it comes with a price. We do have the normal time slot for this one here, but it would be the first day. But the advantage of that is you'd be fresh mentally. Just think about it. We can decide something tomorrow. And then that would be Monday. So in other words, our final would then be, if we do that, the final would then be next Monday. And the only reason I'm saying this is that then you'd be mentally fresh. You're hitting it strong. You wait to the end, and I just know from experience, at the end of finals week, people just want to get out. And it's just, then you're battling the, I want to get out of here really fast syndrome. And that's not good to take a final. Okay, so we can talk about it tomorrow. Just kind of keep that in mind. Okay, so let's go over what we did last time. And I want to give some examples of this. So, and I gave you the last, did I give you the homework too? I sent you that electronically, right? Yeah. And I printed it out someplace. And where did I print it out? I don't know. I'll give it to you this afternoon, but I did print out a hard copy. How did I put it all together? Okay, so we talked about cross products. Okay, so this is A, and this is B. And we have a dot product. We have a cross product. Okay, this one is always a scalar. This is one that's always a vector. That's why I have to do the magnitude. And how did we define each of these? What did we do with our vector A? Exactly. We took our little A, we dropped a little perpendicular to B here, line. And this part here, we call A parallel. So this is the part of A that's parallel to B. And this part right here, this is a component of A perpendicular to B. This is theta. And how do we define a dot product? A dot product is always A parallel times magnitude of B. And then if you put in your A parallel here, if you say that this is magnitude of A cosine of theta, that gives you the AB cosine of theta. What did we say about the cross product? It is by definition A perpendicular times magnitude of B. And this is again going to be your A, B, sine of theta. Now, how did we say we find the direction for a cross product? We use the right-hand rule. So how did our right-hand rule go? Okay, where do your fingers go first? So if we want this one here, we want C equals A cross B. I'm just going to make one up here. Let's say this is A. Let's say this is B. What does that X with a circle on it mean? He's into the board. So how do you do your right-hand rule for this? Your fingers have to go in the direction of the first. So the A is coming first, so your fingers go in the direction of A. And then what do you have to do? You have to bend them in the direction of B. So this is AB. So it's A crossed into B. So then your vector goes like this, C. What do you know about this right here? Any cross product must be perpendicular. Yes, this must be perpendicular to both A and B. If it's not, then it ain't a cross product. It's something else, but it's not a cross product. And what did we say we use this for? Torque. So we had a rod here. Here's our pivot. And here's a force like this. This is F. And what do we call from the pivot to where the force is applied? That is called? Okay, it's called the moment arm. Good. Okay. And then we say that which part of this F is causing rotation? The F perpendicular part. So I could take this F, I could break it up into part parallel to R and perpendicular to R. And this part here, the F perpendicular causes rotation. And so, am I still on the board? I am. I'm still clear. Woohoo. Okay. So we define the torque, and this is a symbol for torque. It's basically the Greek letter tau. How did we define it? Yeah, magnitude of R, F. Well, the F perpendicular, which is going to give us the F sine theta. So it's going to be this guy here. We said, hey, this is nothing but magnitude of R cross F. So torque is by definition R cross F. That's for a single force. Okay. So now what I want to do is I'm going to kind of do this a little bit in a backwards fashion, but for those of you who are mechanical engineers, you're going to need this. So I'm going to hit this part fast or hard. What I want to do now is talk about equilibrium. Let's do an application right away. Who are the mechanical engineers again? 1, 2, 3. Okay. You're going to have a whole course in statics on this, and you're going to be doing this all the time. And I want to show you something that isn't normally done, but I think the professor who teaches it always has you draw certain pictures. And so I want to just kind of go over this one point so that when you see it in your class, you don't go, huh? Because it's not that hard of an idea. I want to talk about static equilibrium. And just so you know, if you can say static equilibrium, you can also just say statics. You can just say equilibrium. These are all the same thing. Doesn't matter how you write it. So the question is, what are the conditions for an object not to move? Okay. One of them we know. What would that be? You want, okay, your grades on last week for this one, sorry. So if you want something not to move, what has to be the condition? I didn't hear what you had said. You said no. Okay, so this is one, that your net forces have to be 0. And there's something else. So let's consider this here. Let's say here's a rod, and let's say I'm going to grab it here. This is my pivot. I'm going to pull down here with some force F. I'm going to push up here with some force F. What is the net force on this? If I push up with the force F and I pull down with the force F, what's the net force on this guy? Zero, because there's a positive force, then there's a negative force, no net force. But what would this object do? It's going to rotate. So if I don't want this thing to rotate, okay, now to rotate it, you have to put a torque on something. What's going to be the other condition? Really? That you want the net torque to be zero as well. So there's two conditions here. This is one of them. The other one is your net torque has to be zero. There, that's it. You're gonna have the whole course on that. Now you're gonna do a fair amount. You're gonna worry about if you have like a bridge, you have forces on it, you want to figure out whether this component's gonna actually start to buckle on you and stuff like this. There's a lot you're gonna do with this. But this is what you do in the course. So let's do an example. So let's say here's a wall. And here's a beam. Okay, and I'm gonna have a let's say I have a wire go like this. This is a wire. Let's say this is a 30-degree angle. And let's say here I have a I don't know, 50 kilogram mass. And let's say here I have Yogi. This would be a picnic basket because it's Yogi Bear. Hooray. That's just fun to do. Okay, so here's Yogi. Let's say that this rod is, let's say that this is a big rod. Let's say this is 10 meters. Let's say the mass of the beam. Let's say it's 20 kilograms. Let's say the mass of the of Yogi. I don't really know what a bear weighs, but they're pretty big. He looks like a pretty big bear. Let's say 200 kilograms. And let's say Yogi's out here 3 meters. For part A, I want you to draw the free body diagram for the rod. Well, let's say for the beam. What would be all the forces acting on that beam? Now start off by drawing this. Going where? Yeah, when you do this, you have to draw the forces where they're applied. If you don't, nothing's going to work here. So that tension is connected here, so we have to go like this. Tension in the wire. What else? Yeah, there's a wire here, but what do you know about the tension in this wire here? The wire here is going to have to be the same as. Right. If we look at this sign here. If I had to say draw the free body diagram for this little sign here, what would you have? You have some tension from the sign and the mg down. If that's just sitting there, what do you know is going to happen? They have to be the same, right? This has to equal the mass of the sign times g. So I'm just going to write the mass of the, I'm going to say the mass of the sign times g. I'm just going to call it ms. This would be mass of the sign times g, but it's really acting through this tension here. It happens to just be this. Okay, keep going. Okay, so we're going to have the mass of Yogi here. This is the mass of Yogi times g. I can also assume a uniform beam. Yep. So, where is it going to act if it's a uniform beam? Yeah, there's something we haven't talked about yet, but I'm just gonna, I'll try to develop it later on. That if you have some object, let's say here's some generic object. There's gonna be a point that if I could somehow put my hand in this object here, I could actually balance that object on my finger. And that point is actually called the center of mass. So basically I can treat this object as if all the mass are at a certain point here. This is the center mass of this, CM. And this would be the point of that I could somehow put my finger here. I could balance that whole object on my finger. That's what that is. And so what's going to happen if this is a uniform beam, that center mass has to be at the center because it's uniform. So this is going to be at the center here. So this would be the mass of the beam times G. Is there anything else on this?
Pushing against the wall and the wall instead of.
Okay, so there's going to be the force that the wall puts on the beam. How does that go? I don't have a clue. So if you don't have a clue what it's going to do, we're going to just draw it like this. If the x component turns out to be positive, that's good. If the y component is positive, then we have the right direction. If not, we're going to have to flip it. So if we don't have any clue what it is, I'm just going to randomly draw it like this. So this would be the force from the wall. Maybe it's going like that. Maybe it's not. We just don't know yet. Okay. Any questions to that? Okay, now here's the thing that your professor when you take statics is going to have you do. Okay. Draw the vector, the force, the vector force diagram. In other words, take all those forces and add them together. So if you were to add these forces all together, what would that look like? Which vector do you want to start with? Let's start with the vector. Here's my tension. Okay, let's add the force of the wall. How do vectors add again? Tip to tail. This would be the force from the wall. I don't quite have the scale here, right? Now, how do the other forces have to go? Again, if that beam isn't moving, what do you know about the total force?
0.
Has to be 0. So where do those, when I add in this and this and this, where do they have to go? Yeah, they have to go down here. So this would be the force of the sine, force of the beam, of the weight of the beam, plus the mass of Yogi, the bearer times this. This right here has net force with a 0. So she's going to do, from as far as I can tell, my students who have had her have taken her courses, she'll have you do a lot of these diagrams here, where she was going to want you to take all the forces acting on here, and then adding them up and basically seeing that you get this sort of diagram here. And then she's going to do a lot of analysis with that picture. Okay. I hope there's a part C to this. Yeah. Find the tension in the wire. And so what's the condition for this wire, for this beam not to move? Yeah, you're gonna have to say all the forces equal 0. So the net forces equal 0. And what's the other condition? Your net torque, meaning if you add up all the torques. Now let's have to get 0 here. Now, how do you calculate the torques on this system here? What do we say torque is?
Perpendicular to R.
Okay. I'll always put the R first, even though in the magnitude part that's going to work perfectly fine. But just to force a habit, makes when you put the R first. So it's going to be that R times the magnitude about perpendicular as a vector equation. It's what? R cross F. So what is R again? And it goes from where to where? From your pivot to where the force is applied. Now in this case here, since it's not moving, I can pick any pivot I want. I could say I'm gonna have my pivot be here. Perfectly good, really stupid, but a perfectly good spot. I could pick up here. I could say my pivot is here. Again, perfectly valid, really stupid. It turns out when you do these problems here, there's gonna be one part that's a lot better than another. And there's gonna be a really great spot to pick my pivot, because it's gonna save us a whole lot of time. It's gonna allow us to get the answer really, really quick. So where would be a good spot to pick my pivot here and why?
Where it attaches to the wall.
Correct. Why? Okay, let me write down the thing and then we'll figure out why, but that's completely correct. Okay, so we know the net torque. So if I want that net torque on that rod, what does it have to be? It's gonna have to be the torque from the wall plus the torque from Yogi plus the torque from the sign plus the torque from the beam itself plus the torque from the tension. If you add those all together, what does this have to equal?
0.
This has to equal 0. Tell you what, this is going to be easy to calculate. What's going to be really easy to calculate the torque from Yogi, which is just fun.
You know the distance between the wall.
Yeah, that if I take this to be the pivot here, I know the distance from here to here, that's my R. What force does Yogi put on the wire? To the rod?
200 kilograms. Mass
Times G. Okay. So this is going to be really easy to calculate the torque from Yogi. How about from the beam?
You know, it's in the center, so it's
Yep. So that's going to be easy. What about from the sine? Yeah, it's going to be this will be easy. What about from the tension? Okay, so we know the R.
we have our
We have our angle, so we can find. Keep going. We can find the T perpendicular. Okay, so I can write an expression for this and all these other things. I don't know what that tension is. That's not good. Okay, but why is it really great to pick this to be the pivot? Because I have no clue what this force of the wall is. So why would I maybe pick that right here? Be my pivot. So the torque, if that's my pivot, is 0. What happens is if I make this a pivot, this is my pivot right here. So here's my pivot. If I look at the R for the wall part, what's the distance from the wall here to where the forces from the wall is applied? 0. Right? There is no distance from here to where that force is. So the torque then from the wall has to be 0. So why did I pick that? And it completely eliminates one whole thing here. If I had picked over here to be my pivot, let's say I call my pivot right here at the end here, then what would that get rid of? Torque from the tension and the torque from the sine. Now, since I want to find the tension, I want to find the tension in the string, I'm going to use that one here. And again, you can see that. Remember when you had the door here? In this case here, the door is hinged like this. So here's my natural pivot. If I take my force, and if I put it here on the right here, how much is the door moving? It ain't. How come? Because the moment arm is 0. Okay. So let's go through and do this. Now, when you do these, you need a sign convention. Okay, we have to have either clockwise or counterclockwise being positive. Okay? It doesn't matter as long as you're consistent. So do you want something that causes a clockwise rotation to be positive? Or you want something that causes a counterclockwise sign rotation to be positive? It doesn't matter. I'll go with the first one here. Counter to be positive? Okay. So Carter says we're going to use that one. Okay. So that one, let's go through and calculate this. What would be the torque due to Yogi then? -3
Cross
Okay, so when you do this here, remember any torque is R cross F. That's the torque from any force. So if I look at the magnitude of this right here, this would be the magnitude of R, magnitude of F, sine of theta. Okay, if I look right here, here's my R. What angle does this R make with Yogi?
90 degrees.
90 degrees. So the sine of 90 is 1. So the torque from Yogi is going to be 3 times the mass of Yogi, times the weight of Yogi. And why is it negative? Because if here's my pivot, which way would this cause a rotation?
Phys.
That would cause a clockwise rotation. So this is going to be a negative torque because it's against my sign convention. So the mass from Yogi, the torque from Yogi is going to be minus 3 times the mass of Yogi times G. Okay? If I were to say the direction from the right-hand rule, if I were to say draw the vector for the torque from Yogi, what would that be? Up, down, right, left, and out? I'm hearing it out. How does the right-hand rule go again? Point your fingers in the direction of R, then cross them into the direction of F. So here's R going this way. So what do I do with my hand? It has to go this way. This is R. How's my force down? Down. So R cross F, that's into the board. So the torque from Yogi is into the board. I've seen this problem at a different school before. It's actually the first place I started teaching, and I drew this little picture, and I went, this is a really easy problem to do. All we have to do is we have the bear, we have the beam, the BEAs cancel out, and all we need to do is figure out the ratio of R over M. And this kid raised his hand and went, does that always work? But sure. Always. Yeah. I wasn't expecting that. Wow. Okay, so that takes care of this fellow here. Tell me about the torque from the sine. Was it minus? Yes, here's my pivot. That force is coming this way. That's going to take this and try to call it a clockwise rotation. But we're arbitrarily saying counterclockwise is positive. So it does negative. Okay, the R is 10. Yep. Mass of the sine times G. Okay. Okay, tell me about the beam. This B. The length over 2. I'll just put like that to make it kind of emphasize what I'm doing here. Okay. Times the mass of the beam times G. Okay. So this is this guy. This is this guy. Now we need the torque and the tension. This is 30 degrees. So what do we have to have? Is it a positive torque or a negative torque? Positive. What direction does it go? Up, down, right, left, and out? What's the direction of the torque? The vector torque. Up, down, right, left, and out. R crosses into F, comes out of the board. Okay. Now, let's go through and get the magnitude over here. So what is this going to be? This is going to be the R, which is 10. Okay. Times, now I need that F perpendicular, which is going to be what? The T times the sine of 30. This is my T perpendicular. If I add all these torques together, what does this F equal? SB 0. So I take all this stuff to the other side and divide through by 10, and divide through by sine of 30, and that's my answer. So this gives me T equals 3 MYG plus 10 MSG. It's 10 over 2 MBG, all divided by 10, sine of 30 degrees. I have no idea what this is going to be. I'm going to call it star. So if you're a mechanical engineer, why would you even care about that tension? Presumably, what don't you want to have happen? It'd be really nice if that wire didn't break and then that sign collapses and then kills some pedestrian on the ground, okay? So what do you have to do? You'd actually have some maximum strength for that wire. That basically some tensile strength for the wire. And that's why you'd have to calculate that to see whether that's actually within some safety parameters of the wire. Okay? Make sense? Okay. I hope there's a part D to this. Find F wall X, F wall. I want to find the X and Y components. This right here. So how would I do that? Okay, would be a good place to pick it. Yeah, I could take right here to be the pivot. I could do the calculation. And that's going to give me the magnitude of F wall. And that's the problem. I mean, that's completely correct. And I get the magnitude then the force from the wall. You have no idea what the theta is, so you can't figure out what the X and the Y values are. That beam isn't moving. Is there another condition? The net force S equals 0. So you're also going to know this. If your net force was 0, and I can break this up into F net X equals 0, then F net Y equals 0. So let's look at all the forces in the X direction here. So I'm going to redraw that. That picture is a little cluttered. So I have this. Here's my force from the wall, and I can break this up into an F wall X and an F wall Y. Here's my MYG. Here's my MBG. Here's my MSG. And here's my T, which I can break up into a TX and TY. Okay, what are all my forces in the X direction?
X wall, T X.
Yeah, these two forces here. And if it's not moving, what do you know about those? They would have to be? They'd have to be the same, equal and opposite. So I'd have to have the F wall X, that's equal TX. So this would be T times the cosine of 30 degrees. Okay, if you're a mechanical engineer, why would that be really important? Right? This beam is under compression. You're pushing both ends. What don't you want that beam to do? You don't want it to basically buckle of any form. You want it, there's going to be some compression on it, and we want to make sure that that beam can actually then take that. So you know what the material is, and then you look at basically the tensile strength of that material, then you can actually kind of figure that out. Okay. So that's actually why it would be really, why you have to really worry about this. Okay, what does this one give you?
The math is minus T.
Yeah. So how do you get that? Well, you said the force is going up. This force and this force are going up. Well, the forces going up have to equal the forces going down, but that's not moving up or down. So this would have to be equal to the MYG, let's say MBG, let's say MSG. And so this Y component from the wall would be this, all these masses put together. pull out the G. Now take over this one here, which is this T sine of theta. Then that would give you this value here. And that's how you do that. If one of these turned out to be negative, what would that mean? Let's say this one turned out to be negative. Yeah, it means that we basically made the drawing was wrong here. It'd actually be going down like this. Questions? Okay. So we'll do more of these here, but I'll leave this here. I want to get another topic that's a little on the tricky side. Now we have enough time for this. Okay, I want to ask a question here. I want to ask if an object is rotated about some point, what is its kinetic energy? Okay, so here's some big blobby thing, doesn't matter what it is. Okay, and here's a pivot. I'm going to rotate it like this at some omega. What did we say omega is again? Okay, give me a name for it, first of all. Omega is the angular velocity. We're going to get angular momentum in a bit. So this is your angular velocity. How do you define it?
Thing over a period.
Not quite. D theta dt. What are the units for this? Well, give me the practical units. Let's say you work at a garage. Car comes in. Yeah, revolutions or rotations per minute per hour, something like this. The MPS unit is going to be basically radians per second. The radians don't really have units, but for all practical purpose, if you have like this engine that's just spinning at some ridiculous rate, it's always going to be in terms of revolutions per minute or hour or something like that. Okay, that's rotating. So the question is, what is a kinetic energy then of that mess? This is a little tricky. Okay, we only have one kinetic energy expression. What is it?
That's mv squared.
1/2 mv squared. So we only have one kinetic energy expression. We only have this. Now, what's the problem with saying, okay, I'll know if I know the mass of this object, and figure out V, I'll use this. What's the problem with this? What?
V.
That's true if you're more explicit. That's going to be the fundamental problem. I mean, that expression is correct, 1/2 mv squared. All right, so I'll move it like that. I know the mass of this. If I know the velocity of it, the kinetic energy marker is 1/2 mv squared. Perfect. What's the problem though if I rotate it like this?
With acceleration.
The distance from your pivot to each point is different. So if you have a point farther out, it's moving faster than something farther in.
Exactly. If I go like this, if I rotate this, what's going to happen? The further out I go from my pivot here, these velocities are actually larger and larger and larger. Remember the record equation? Remember when we had the record? Here's the record. Right. Here's a point here. This is point A, B, and C. The velocities are like this. Velocities increase the further away you get, because remember what we showed is that we know that the velocity equals this r times omega. So this is the omega of this guy here. So what's going to happen here is that basically all these different points here have a different velocity. if I have a point like right here, there's one velocity, I'll call this one, V1. If I'm out here, I'll call this 2, that has a bigger velocity, V2. I'm way over here. Well, that 3, that has an even bigger velocity, V3. The question is, and what do you have to do? And we're going to do this all the time next semester. All the time next semester. We've seen this trick before. What am I going to treat the subject as being made up of? A whole bunch of little points. So I can calculate the kinetic energy for one tiny little point. And if I want the total kinetic energy, what do I have to do? I have to add them together. Hey, how do we add them? How do we add together a lot of little points? An integration. And you have to integrate over this whole animal here. So what we're going to do here is the following. We're going to have this big mess here. Here's my pivot. I'm going to come over here to some tiny little point here. I'm going to call this R. And I'm going to call this mass here. I'm going to call it dm. Why am I going to call it dm? A d in front of something means some small amount, some tiny amount. And this has some velocity here, v. Now I can write the tiny kinetic energy for that little mass. And so what would be the tiny kinetic energy for my little friend there? One half. The mass dm times the velocity is v squared. Hey, do I know anything about that v for that little friend? If this is rotating at some omega, that's our omega. So this v is our omega. If I put this in here, I get 1/2 dm r omega squared. So I can write this as 1/2 dm r squared omega squared. And if I want my total kinetic energy, what do I have to do?
To however far up it goes.
Okay, so you're right, but we're not going to put in limits. We're just going to say over the whole object. You're all knowns in Calc 3 yet, right? Okay, so we're just going to say over the whole object. When you actually take Calc 3, it turns out it's going to be a 3-dimensional number. Well, we're not going to worry about that. So if I want the total kinetic energy here, this object, it's going to be the sum of all these tiny little kinetic energies, which is going to be 1/2 dm r squared omega squared. And this is over the entire object. What we're doing here, we're going to treat the object as a collection of small point masses. Yeah. We find the kinetic energy of one, then we add this one up, we add up this guy here, we add up this guy here, we add up this guy, we add up all the little point masses. That's going to be the total kinetic energy for this guy. Okay, what comes out of this integral? Oh, there's an obvious thing. What comes out of this integral here? A half. Okay, so we get the half out. Okay. There's one other thing, but you have to think about it. Can the r come out? Because it's not constant. The r is all over here. The r can't come out. We can't pull out the dm because we're integrating on dm. But what do we know about is true for any of these masses here? They all have the same. They all have the same omega squared. So I can pull out the omega squared. You get this dm r squared. Now this mess right here, that mess right here occurs all the time, and we call this the moment of inertia I. So this is the moment of inertia. What we're left with is that the kinetic energy for this thing is 1/2 I omega squared. And that's gonna be the rotational kinetic energy for an object. And so we're gonna meet together at 1:20 for lab today, but again, we're not having lab. We're gonna have a series of 2 lectures. What I wanna do is give you a sense of what this eye is. Because this eye is a nasty little piece. And just so you know, if you're a mechanical engineer, okay, this eye ends up becoming basically a 3x3 matrix. And it turns out that if you want the fancy schmancy name for this is actually something called a second rank symmetric tensor. So right now they're just words, don't worry about it. But it turns out there are a lot of other animals that live in the physics zoo between vectors and scalars. And this thing is not a vector, it is not a scalar, it's an element of a second rank symmetric tensor. Don't worry about what that is, okay? But it turns out, if you take the course in upper level mechanics, or take your upper level physics course in classical mechanics, that's a nasty little animal. That has teeth. That has actually serious teeth. Okay, have a good day. See you this afternoon.